Hey everybody. So in this video, I'm going to walk us through doing some of the most common non-parametric equivalent tests in R and RStudio. And these will be equivalents of the independent t-test, paired t-test, independent ANOVA, and repeated measures ANOVA. So let's get right into R. Now, here we see we've got our file that's got our script that we've been using up to this point. I have tried to add as much comment into the previous set as I could, just to make life a little bit easier. So the first thing I'm going to do is create a new section, and this is going to be for non-parametric tests. So I just use the pound sign to create a comment, and I'm just going to call it non-parametric statistics. Okay, so now I've got a new section here that I've started. So the first thing we're going to do is going to look at the non-parametric equivalent of an independent t-test. So that just involves testing whether or not a variable is different between two separate groups. So what we're going to do is we're going to import the data set, and it's called apathy.csv. And I'm just going to call it apathy.data. It's got headings, and it looks good. I'm going to import, and this is what the data looks like. What we have is two drugs, ecstasy and alcohol, and people who took that, and whether or not they had an apathy score, which meant do they want to just hang out on the couch and watch Netflix all day instead of doing something productive, what their score was in apathy the next day after taking either alcohol or ecstasy. And these are obviously two separate groups in this case. Now, we do also have the same thing for different groups, whether they did that on Tuesday and their apathy scores for Wednesday. But we're not going to worry about those right off the bat. So one of the first things you're going to need is to use a package called R-Companion. Now, if you don't have this installed yet, you're going to want to use that and load that up as a library. I'm just going to type in library R-Companion, and that will load that up in terms of that package. Okay, so the next thing we're going to do is create a set of commands. I'm going to use just an old sort of framework here that has an attach and detach. Just makes my life easy. I'm going to copy and paste that there, and I'm going to remove all of the commands, and I'm going to change this. This is going to be apathy.data, and of course I'll label that so we know it came from apathy.csv, so we can remember for next time. Okay, so now we attach that data frame, and we're going to do a couple of things to it. So the way to run our test that we're going to do in R is by using a command called Wilcoxon.test. And all I need to do is tell it what I want to look at. We're going to look at apathy Sunday as a function of drug. So I go back here. I need to give it AP_sun as a function of drug. Now, if I run that, we should see that I got a Wilcoxon rank sum test with correction. Now it gives me a bit of a warning message because it can't compute exact p-values with ties, but we're okay with that. We got a Wilcoxon W, that's our test statistic, of 35.5 and a p-value of 0.2861. So here, this is a not significant result. So there's not significant differences between these two drugs on Sunday. Now, perhaps before that, I should have actually run a test to see if we've got significantly non-normal data. And remember, the way that we do that is by using a tapply function in this case. So we want to do a tapply. So I'm going to apply a function to two separate columns of data. And that's going to be AP sun, comma drug. And I want to do Shapiro.test. All right. So if I run that, we should see that what we get out is a Shapiro-Wilk normality test, and we see our p-value is 0.019, so significantly non-normal, giving us a good reason to actually run the non-parametric test. So let's do this same test for the people, the different groups that did this for Wednesday. Now, it should be reasonably easy. What I could do is just copy this if I like, paste it, and I'll do the same thing for Wednesday, WED. It's the only thing I need to change. And now I can run the whole thing. I'll get everything out for Sunday and Wednesday. So for Wednesday, we see that for alcohol, we've got significantly non-normal data with a p-value of 0.003. And for ecstasy, in fact, our p-value is 0.565. So it is not significantly non-normal. But because of this, we're still going to run that Wilcoxon W, or the Mann-Whitney test. Now, what that does is that gives us a test statistic with a Wilcoxon W of 4 and a p-value of 0.00056. Now, what this suggests is that there's differences in apathy scores on Wednesday, depending on whether you took alcohol or ecstasy. So if we want to have a look at what that data looks like, we can just do a box plot. So box plot in this case of AP underscore Wednesday is a function of drug. And I'll run all of that as a command. And we should get, I put a comma, it should have been a tilde as a function of drug. And we see I get a box plot in behind me, and we can see that ecstasy apathy scores were significantly higher than alcohol apathy scores. Now, what I may want to do is run an effect size calculation on that Wednesday data. The way I'm going to do that is by using a command called Wilcoxon R. It's that one, Wilcoxon R. Don't get it mistaken for the OR. And I need apathy scores Wednesday, comma, drug. Now, if I run all of that, what we see is I get all of my commands out, including my test statistic, but now I've got an R score of -778. So that's pretty much how we run the Mann-Whitney U, or a Wilcoxon sum ranks test. And what we're going to do is now run a test for repeated or paired data. So if we were trying to do a non-parametric version of a paired samples t-test, what we would use is the next thing coming up. So we're going to load a file called apathy.csv. So this is, imagine we had the same people who took alcohol or ecstasy. So we've got these two different groups, but we've got the same people that, for example, that ones that had alcohol, and we want to test their apathy scores on Sunday and then follow up with them on Wednesday and see if their apathy scores have changed. And we could do that with the same, we could do the same thing with the group that took ecstasy. We could check their apathy scores on Sunday and follow up with them on Wednesday. And we're going to test that by using two separate paired samples t-test. But in this case, the non-parametric version is the Wilcoxon signed ranks test. So I'm going to load up that data set, import data set from text, apathy today, and I'm just going to leave it with the name apathy.today. And that looks all good, and I'm going to import. Now what we see is we've got Ecstasy Sunday and Ecstasy Wednesday, and we've got Alcohol Sunday, Alcohol Wednesday, and we've got scores for each of those. So first thing we want to do, we're going to copy this entire block of data, and we're going to see if there's anything we need to do with this. And we're going to just get rid of the commands in the middle, and we're going to attach the data frame apathy today from apathy.csv. So the first thing we're going to do in this case is it uses Wilcox test again. So it's the same command that we had up here, but now what we need to do is we need to give it, for in this case, let's do for Ecstasy Sunday, and then we need to tell it Ecstasy Wednesday are our two columns that we wanted to compare, and then we tell it paired equals true, and we're going to ask it to not correct for any issues that it's got. So correct equals false. So let's just run that on its own and see what we get. So we see it gives us a warning message that tells us it can't compute exact p-values when there's zeros, which is fine. And it gives us what's our V statistic here, and calls it a V, but it's really just a Wilcoxon signed rank, a p-value of 0.011. So significant. So let's do the exact same thing for alcohol data. So if I use Wilcox test, now instead of ecstasy, it'll be alcohol, alk, sun, and alk, wed. And I can run all of that. And what we see again, for ecstasy, I get a p-value of 0.01. And for alcohol, I see I've got a test statistic of 47 and a p-value of 0.0465. Okay, so in this case, now I might want to have a look at what the data looks like. So let's do a box plot of the entire data set. Apathy.today. In fact, I'm just going to run that command on its own. Control Enter. And I get a box plot, and behind me, what we can see is that from Sunday to Wednesday, the apathy scores for ecstasy went up. For alcohol, they in fact went down slightly. Okay, so the last thing I might want to do is I'm going to use a new command in order to get my effect size scores. Now, the problem is that it's really sort of difficult to do this. I need to try and put out some different types of values, get some Z scores, etc. And there's been a function written, and I'm going to copy and paste that into this sort of setup here, which you can copy later on. And that will give you that function. So you'll be able to download this script, and there'll be a link in the description. So in order to create this new function, we're going to use the command here. I'm going to paste it here. There's a bunch of commands, and this is actually from Andy Field in his textbook. And essentially it creates a new function called R from Wilcox. And it takes the stats from the Q norm from the Wilcox model that you specify, finds some Z values, puts them into these different parameters, and then creates an effect size and output for us. So what we need to do is we need to specify a model, and we need to specify the n, or the number of observations in this case. So in order to use this function, the way we do it is going to be R from Wilcox. Now because it's in there, it sees it. And I need to give it a function of a model that it's going to need to look at. But remember, I just printed out the outputs of these. I haven't put them into a model. So I'm going to create a new object for the first one called ecstasy, or just EX. And my other model, I will put the Wilcox test into one called ELK. So now I'll have put these tests into these objects, and then I can take the R from Wilcox and apply it to those objects. So it would be X, 20. And then I can also do an R from Wilcox for ELK, 20. So when I run all of this, I get an error because I actually haven't run this part of the command yet. So I still need to run all of this in order to create that function. So now we have R from Wilcox function here that I can use. So now I should be able to run this and not get those errors. So we see what it's done is it's given me those same warnings that it can't compute exact p-values with zeros, but hasn't output those models because I've just put them into these objects called X and ELK, and it's only actually given me the R effect size, 0.56 and 0.44, both of them negative. So the last thing I want to do, if I want to read these models, I can just output the model name, EX, and then ELK. That way it will report those outputs for me. We can see here it gives me the Wilcoxon sign rank test now for both of those with my p-values and my test statistic, as well as my effect size that I can report down here. Okay, so let's move on to doing what would be a non-parametric equivalent of an independent ANOVA. So the first thing I need to do is import a new data set, and it's going to be called soyawanttodoatest.csv. And I'm just going to call this soy.data. Import. Now, what we can see is this is soy meals per week, and the values are 1 through 4. And we have our dependent measure is sperm count. And this is going to test the hypothesis that increasing number of soy meals per week leads to decreased sperm count in males. Now, for this test, we're going to use a function or a test called the Kruskal-Wallis test. Now, I'm going to just copy my framework again and get rid of everything in the middle. And we're going to load up soy.data. And this comes from soyawanttodoatest.csv. All right. So the test that we're going to want to do, like I said, is called the Kruskal-Wallis test. And we're going to need to load up a couple of libraries before we're able to do these things that we need for this one. So the first library that we're going to be using is actually called pgirmess. If you don't have that, just make sure to download it by going to the packages and clicking on install. If you just go pgirmess, it will install. I'm going to hit Control Enter, and that has loaded that library. Okay, so the next library that I'm going to use, we've used in a previous video, and it's called R statics. Now I'll just Control Enter to load that package. Okay, so in order to do the Kruskal-Wallis test, I use the command Kruskal.test that we see here. And the way that we give it parameters is the same way we've done it before. So it's going to be our dependent measure as a function of something else. So sperm count as a function of soy meals per week. We look back up to soy data. We've got soy underscore meals per week and sperm underscore count. So we're going to do sperm count as a function of soy meals per week. Let's also do a box plot of that exact same thing while we're at it. So instead of Kruskal test, we do the exact same command, but just using box plot. Okay, so this will give us our test and a box plot of that as well. So if I run that, what we see is a box plot behind me where it looks like the sperm count's a little bit higher and starts to go down and gets a little bit lower here by the time we get up to 4 soy meals per week. Our Kruskal-Wallis rank sum test gives us a chi-squared value of 8.6589 with degrees of freedom of 3, and our p-value is 0.03419. So there's a couple other things we can do here. We can ask it for an effect size of the overall Kruskal-Wallis test. So that's where some of these libraries come into effect. The way we're going to do that is by going Kruskal underscore F size, EFF size, and it's going to be on soy.data with sperm count and meals per week. Another thing I can do is do some post-hoc tests all in one shot. Remember, we know there's a difference somewhere in these 4 groups. We don't know where that happens to be. Now, we may want to test simply if 2 meals are greater than 1, or 3 is greater than 1, and 4 is greater than 1. Maybe that's the most important test we want to do here. So what we can do is actually use a command called Kruskal MC for multiple comparisons. And now what we need to give it is the same arguments, which is sperm count and meals per week. I need to tell it the data. And I need to give it a command that tells it two-tailed. And I put that in single quotes. All right, so I should get an effect size, and then I should get some multiple comparisons now for this test. And if I run that entire set of commands, what we see is I get my rank sum test. Now I get an effect size, which gives me an effect size, which is an eta squared of the h is 0.0745. And it tells me that's a moderate effect size. We can also see that it's given me the observations of 1 versus 2, 1 versus 3, and 1 versus 4. And it's telling me whether it's exceeded the critical difference by telling me whether or not that's true or false. And only the difference between 1 meal and 4 meals is significantly different in telling me that's true. Now there's a couple other ways we could do these post-hoc tests. Remember, we could do a Mann-Whitney U on this, or it's using the Wilcoxon test. So we can do a Wilcox test, or we can do a Dunn's test on these. And I'll show you how to do both of those. So in order to do the Wilcox test, so we give it the command Wilcox _ test here. Note that's slightly different than Wilcox.test that we used up here. I need to tell it the data set we want, which is soy.data. And then I need to tell it the contrasts that I want to do, or the values and as a function of. So again, it's the same thing. It's sperm count as a function of soy meals per week. And the last thing I'm going to do is give it p.adjust method equals, and I'm going to say none in this case, because we're going to do the correction manually using a Bonferroni correction. The other one I can do is the done _ test. And it is structured in the exact same way. So I just need to give it soy data and all of this. So now when I run all of those commands, we see now I get my original post-hoc tests. And I also get now p-values for all of the different comparisons. 1 versus 2, 1 versus 3, 1 versus 4, 2 versus 3, etc. And I can look over here and determine whether or not that's significant. So because it's no adjustment been made, I see I've got a p-value of 0.009 and a p-value of 0.035 here, and p-value of 0.016 for these individual Wilcox tests. But remember, if we're just going to be doing the test between 1 and 2, 1 and 3, and 1 and 4, that means that we've only got to do 3 different comparisons that we're going to look at. And if we do that, we want to have a critical p-value of 0.016667, whatever, because it's p-value 0.05 divided by 3. So it would seem in this case that if I just made those separate comparisons, that 1 and 4 would be significantly different from each other. 2 and 4 are not significantly different than each other. Now, of course, I could do this same thing with a Bonferroni correction, but then the Bonferroni correction is going to correct for all 6 of these, and it will turn out that none of our comparisons are significant. And remember, if you wanted to, you could break this down and you could do separate Wilcoxon tests for each of the different comparisons that you wanted to do. But it's easy to do it in this way. This Wilcox test gives you the exact same thing as if you had done all the individual tests. Okay, so for our last one, we're going to do a non-parametric equivalent of what would be a repeated measures ANOVA. And that's the Friedman test. And in order to do the Friedman test, we're going to use a data set called diet.csv. And I'm going to import that. I'm going to call it diet.data. And it does have headings. I need to specify yes. And I'm going to click on import. What we see is we've got a data set of people's weights in kilograms at the start of doing a diet, and then after the first and second months of doing that diet. And we want to see if those individuals' weights change over the course of the diet. If we do tests of normality on this data, we'll see that it's not normally distributed. And what we're going to do is use a non-parametric test called the Friedman's test in order to run our stats on these data. First things first, we need to load a couple of packages for this. So the first package that we're going to want to load is the same as what we did in our last component. It was PGIR mess. So you're going to want to use this if you're also going to be doing Friedman tests. The other one that we're going to need is called desk tools. So DESC capital tools. If you don't have that, just make sure to install it. So now those are loaded up. The next thing I can do is I'm going to grab my framework, copy and paste it. My data frame that I'm going to be working with is called diet.data. And again, it's from diet.csv, just to give you an idea of where that came from. Okay, so in order to run these tests, the first thing we're going to want to do is we're going to use Friedman test. So the command is Friedman.test. And remember I told you that R likes to have data that's in a long format. And here we see it's in a wide format. Now, in order to be able to run this test on the wide format data, we can actually tell R that we need to use this as a matrix and then do it on diet.data. And it will run the test this way. If I run it, you'll see that I get a Friedman rank sum test. It gives me a chi-squared value of 0.2, degrees of freedom of 2, and a p-value of 0.9048. Now, this is the same thing that we saw in JASP and SPSS. However, like I said, in this case, R doesn't really like this wide format data. So let's also import the long version of this data so we can have a look at how it changes when we're using different types. For the Friedman, we actually want to be able to use both types of data in this case, just because it makes the commands a little bit easier. So I've loaded it up in the wide format, and I'm going to now import it in the long format. And it's called diet-long.csv. And I'll leave it as diet.long, and it's got heading, and I'm going to click on import. Now what we see here is we've got subject ID, we've got their weight, and then we've got another column for time. Time 1, time 2, and time 3. And those correspond to the start, month 1, and month 2. And remember, we see each of these subjects, their ID is repeated here. Okay, so back to our command. So now I can do Friedman test in a different way, and it's very much like the way we give the commands to all of our different models. So Friedman.test, and we're going to do weight as a function of time. Remember, diet long, it's weight, and I've got time. But I've also got ID, and I need to specify that it wants ID. So Friedman test requires we use the bar, so that's the vertical bar, it's right beside the backslash, and we type ID. Then I have to tell it which data, because I've already told it to attach diet.data, but I'm going to call it data equals diet.long. Now, if I run these commands, you should see that I get the exact same output from both of these commands. So we see here, I've got the Friedman test from as matrix. It gives me this output. And the Friedman test with the diet.long, and it gives me the exact same output. Okay, so why don't we have a look at what the data looks like. Let's give it a box plot of diet.data. Now I can just run that command separately on its own, and we see behind me I get start, month 1, and month 2. And we see that it looks like weight actually might go up at month 2 in comparison to month 1. Now, we know that there's no differences between these. Our p-value is 0.904. But we might want to use a measure of effect size. And what we can do is use the function called Kendall W. So that's a capital K Kendall W. And we can use diet.data, and that will give us our measure of effect size. And we get Kendall W of 0.719. And that can just give us an idea of what our effect size is here. Now remember, I said that these differences are not significant. But if they were, we would want to do some post-hoc follow-ups. Now the nice thing is, because I've got the data in a wide format and a long format, it means that I can do these Wilcoxon signed rank tests quite easily pairwise. So in this way, we're going to go Wilcox.test, and it'll be start, comma, month 1, comma, paired equals true, comma, correct equals false. And I only have 3 comparisons to make here. So I'm going to copy that. It's going to be start against month 1, start against month 2, and month 1 versus month 2. Now, if I run all of those, I should see that they're not significant, but it gives me all of the signed ranks tests as well. So I've got start in month 1 with p-value of 1, start in month 2, value of p is 0.084, and start and month 1 and month 2, p-value of 0.92. Okay, so that's pretty much all I have in terms of doing all of those tests in R, but you can use that as a base to get yourself started in doing a little bit more complex stuff, or if you have to do some more breakdown of those data.